Okay, for this third part of Lecture 14, we're going to talk about kind of whole stream restabilization and management and armoring. And so, although this number is probably a little out of date because I can't remember, I must have gotten it, it was in the early 2000s, but since 1982, at least according to the National Engineering Handbook, almost close to probably 4.2, $4.5 billion have been spent on about 3,500 stream bank erosion projects nationally. So there's a considerable amount of money being invested in this, and I would guess the number's probably much higher than that now. I was talking with Dr. Penn the other day in Dubuque. They're doing a daylighting and stream restoration project there where they're focusing on these similar things, and that project is running into the tens, hundreds of millions of dollars. So these things can get very expensive pretty quickly. So I want to talk about and kind of define these two types of channels, and then we'll end up focusing on kind of threshold channels for the remainder of this lecture in this class. But I do want to make you aware of designing when we're working in alluvial settings as well. So first I'm going to read this. It says a stable channel is often defined as a channel where the planform, cross-section, and longitudinal profile are sustainable over time. Right? While channel migration may not always be acceptable due to project or site constraints, it's important to note that a natural channel can migrate and still be considered stable, right? So I'll point to that when we get to alluvial channels, right? And so a threshold channel is a channel that's defined basically where the boundary material has no significant movement during design flow, almost any design flow, and you'll see why. And then alluvial streams and channels have beds and banks that are formed of material that's transported, and that could be under many or all flow conditions. There's some material being transported. So that's the difference kind of between these two. You can basically think of a threshold channel as an engineered channel, an alluvial stream and channels as being kind of remaining part of the natural system. So, and we can basically compare and contrast these right here in this table. So we've got some characteristics. Threshold channels, they're immobile at design discharges, where alluvial channels are mobile. That's the that's the stark difference between these two. Bed material and sediment inflow is usually small or negligible in threshold channels, where it's usually significant in alluvial channels. When we think about the dependent and independent variables, some of them are obviously going to be similar, but some of them are going to be very different as well. And when we get to the design equations here, energy, momentum, and resistance, those are all things we know how to deal with. They're easy to calculate. When we talk about alluvial channels, we get into things that are a little bit more complicated or different, things that we're unfamiliar with, including sediment transport and geomorphic relationships, right? So those are other things that we might need to consider in the design equations. And then lastly, here are some design goals. So let's take a look at threshold channels, right? Threshold channels, we have basically applied forces from the flow are below threshold for movement of the boundary material. That's why we call it a threshold channel, right? And so the bed, that means that the bed's typically composed of very coarse material or erosion resistant bedrock. And for us, that means a lot of the engineered linings that we're going to talk about in a little bit. Threshold channels do not have the ability to quickly adjust their geometry because they've basically been engineered or forced to maintain that geometry. And during extreme events, a threshold channel could become destabilized for short periods. That usually comes with harmful morphological impacts, things that were completely unintended because threshold channels aren't supposed to be moving in the first place. Right, and so the design goal of a threshold channel basically is to produce a channel that's got positional or engineering stability. It's not going to move. So here are a couple of examples. Here we can see something that's got a lot of rock or riprap. We've got these big concrete walls that are kind of channelizing water and flow through something. Here we've got a grassed swale, right? So even in design flow or heavy flow conditions, we wouldn't expect this grass to get lifted and ripped out of here. I mean, that would be kind of the catastrophic scenario, right? This bed should remain immobile even at high design flows, and it should remain intact. The cross section should remain there. So should the planform appearance. So I've put up online, you don't have to read it, but it's a pretty cool National Engineering Handbook um, uh, circular or basically guide on designing threshold channels. They've got lots of great equations and things in there. I took this really neat little graph out of the back that kind of shows allowable velocity and then flow duration in hours, right? And so as we look, there are very few things that can withstand high velocities for very long periods of time. Pretty much concrete and riprap are those two things. Once we start getting down to some of these other types of covers, they might be able to withstand high velocities for a short period of time, but once we get to flow durations that start exceeding 10 hours, we can see that the flow velocities, they really must decrease, otherwise we'd start to see failure. So just kind of a neat idea of the different products that we can use for threshold channels, and we're gonna focus on those more in just a little bit. So I'd like to talk a second about alluvial channels, and then after we look at these alluvial channels, we'll pause this lecture amount, and then we'll start talking about the different types of linings that are available to us. So alluvial channels and streams have a bed and bank that are formed of material that's transported by stream under present flow conditions, right? And so here's the Zen quote of the day. A natural channel can migrate and still be considered stable. Now, for many of us as engineers, we might say, that is scary. Like, how do we even figure that out? And it's true, it can be pretty complicated, but there are lots of very neat projects that have dealt exactly with this situation without going in and basically paving over a river or heavily armoring something. So let's take a look at one of them. And if you're really interested in this project, it's a really neat one. A couple of my friends worked on it. It was highlighted by the Federal Highway Administration. You can go to this website and read about it. It was done in 2006. This is the Hoh River. It comes out of the Hoh Rainforest on the Olympic Peninsula of Washington State. And here it comes, and you can see it basically undercut the main route around the peninsula of this highway. It's a federal highway. It undercut it and shut it down. So this consulting firm Herrera was brought in, and between using HEC-RAS models, having experts in geomorphology, having some very interesting structural engineering and geotechnical engineering expertise all brought in, basically what they designed were some huge woody debris or log jam piles that they would use as armoring to basically deflect this flow coming in and push it back into an older channel. So again, it goes back to the Zen quote of the day. A natural channel can migrate and still be considered stable. In this case, through this innovative engineering, they were able to convince the river to stay away from the highway and allow the river to still maintain all of kind of the important functions that it has, both ecologically and with the natural landscape. So there are neat opportunities out there for river engineering. There's a lot of these kind of newer modern designs where we use all the tools that we have, plus some additional ways of thinking about things, and we do really neat, innovative engineering work. Okay, so the final lecture chunk 4, we'll talk about some different types of linings that are available for stabilizing streams. Most of these that we're talking about are for threshold channels because these alluvial channels are kind of beyond the scope of this class. But it'll provide you with kind of a good idea and some reading material if it's ever needed on how to basically line channels.